So what we're going to talk about now are the idea of redox half equations, okay? Half equations sound a little bit strange at first, okay? But basically, what they do, well, firstly we know that a redox reaction, okay, it always involves reduction and oxidation, okay? We know that all redox reactions involve oxidation and, oxidation and reduction. Oxidation and reduction. Okay, and so what we can do to really analyze in depth the way that, a certain substance is oxidized and a certain substance is reduced in a redox reaction is we can write a half equation. Okay, so basically a half equation is an equation that shows just the oxidation part of a redox reaction or just the reduction part of a redox reaction, okay? And so what we can do, what this means is that half equations involve, because we know that we have our acronym, we have oil rig. Okay, so we know oxidation involves the loss of electrons and reduction involves the gain of electrons, okay? And so what we do is we can do a half equation just involving oxidation, okay, and a half equation just involving reduction. And so we can really analyze exactly what's going on and exactly how electrons are being transferred. Okay, so we know that oxidation involves the loss of electrons, okay? So loss of electrons. Okay, so the general sort of format, so E minus apostrophe S, that's electrons. We have to remember to include their charge when we're writing them out in these equations. So oxidation is the loss of electrons. Okay, so the general form of a oxidation half equation is going to be the reductant, okay, because we know that the reductant is oxidized. So it's going to be the reductant. Okay, we know oxidation involves the loss of electrons. Okay, so we're going to have a reductant. Okay, and then that's going to become, one of the products of the reaction. I'll call it product A. Plus, X. Okay, X is just a random number here. X electrons. Okay, so I'm not sure how many electrons are going to be, but it's going to be some number of electrons, okay, because the reductized oxidation involves loss, as we get from oil rig, so oxidation involves the loss of electrons. So as this reductant here is oxidized, product A is produced, okay, and X electrons are also produced, because the reductant is turning into something else and it's losing these electrons, okay. Similarly, okay, we know that reduction involves the gain of electrons. Okay, as given by oil rig, reduction involves gain. Okay, so it's the gain of electrons. Okay, so that means what we have is that the oxidant, because we know that the oxidant is, and yet, try not to get too caught up in the language. It's often very beneficial when we're dealing with redox reactions and half equations to go slowly and think about what each word means, okay? So we've got reduction, okay, and we know that the oxidant is reduced, okay? It's very confusing, so it's best to just really move through it slowly, make sure you understand what the words mean and how they apply to the reaction. Okay, so here we have the oxidant, which is being reduced, okay? And what we have here is that we know that reduction involves the gain of electrons. That means that the thing that's being reduced has some electrons added to it. So we'll call this Y electron becomes product B. Okay, so this is the general format of a reduction half equation. Okay, so these are the two types of half equations you can have. You can have an oxidation half equation, which electrons will be on the right hand side, because in a oxidation reaction, because when something is oxidized, electrons are lost. Or we have a reduction half equation, in which in which electrons are gained by the thing that's being reduced. Okay, and so these are the two formats of the two types of half equations that we can come across. Okay, now the next step is, obviously we've called them half equations, and so theoretically we should be able to add these two half equations together somehow in order to produce a full equation for the reaction, okay? So this is sort of the next step that you'll go through when dealing with half equations. So we're going for the full equation now. Okay, and so what we can do is basically, we know that the oxidation and the reduction are both occurring sort of at the same time in the same reaction. So we can add this equation to this equation. Okay, however, what we need to, if we do at the moment, if we add this equation to this equation, then we will have the reductant, okay, plus the oxidant, plus Y electrons. Okay, and that's going to product A product B and X electrons. Okay, and so unless X and Y are equal, okay, so unless we have X and Y equal, then we're going to end up with an uneven number of electrons in this half equation, okay? And we're going to have equations somewhere, we're going to have electrons somewhere in this equation, okay? And that's something that we want to avoid, okay? Full chemical equations cannot have electrons in them, okay? Because when a reaction occurs, electrons aren't going to disappear to somewhere external, okay? All the electrons are going to be kept together in the reaction, okay? Nothing's going to be lost elsewhere. So that means before we add them together, we can't go straight to this, okay? We can't just add them together like this, okay? What we have to do is we have to make sure X and Y are equal, okay? So for example, if we call this equation 1, call this equation 2, okay, then we're going to multiply equation 1 and we're going to multiply equation 2 by appropriate numbers to make so that X and Y become equal. Okay, so say we have, for example, X equals 2, okay, and Y equals 3. Okay, then what we're going to do, we need to make sure there's the same number of electrons in each reaction. So we need to make sure X and Y are equal. Okay, so what we can do is we can multiply 1 by 3. Okay, so we'll go 1 times 3, equation 1 times 3 gives us 3 reductants, okay, going to 3 product A, okay, and 6 electrons. Okay, so now what we want to do is we want to make it so that equation 2 also has 6 electrons. At the moment, Y is equal to 3. So if we go equation 2 times 2, this will give us 2 oxidants and 6 electrons, producing 2 of product B. Okay, so all we've done is we've multiplied equations 1 and 2 by appropriate numbers, okay, to get 6 electrons on either side. Okay, so now if we add them together, we'll cross that out, and we're going to have 3 reductants plus 2 oxidants, producing 3 of product A and 2 of product B. Okay, and so obviously, you know, we've got these we've been given these half equations. We've multiplied them by, you know, appropriate numbers in order to get a full formula equation. Okay, and so what this means, what this shows us, is that, you know, often if we're given a redox, a redox reaction, if we're given the equation for a redox reaction, it can be quite difficult to balance. Okay, redox reactions can be quite complex. Okay, and so a good way for us to balance a complex redox equation, okay, is to break it down into its 2 half equations, okay, and then multiply the 2 half equations to get the same number of electrons as we've done here, okay, and then add those together, and that way And through that process, we've automatically balanced the reductants, the oxidants, and the products, okay? They've all been automatically balanced. And so this shows that, breaking an equation up into half equations can be a really helpful way for us to balance some complex redox reactions, okay? And so we'll go through an example of this in another video.